Parts to this presentation called Climate Change, Sea Level Rise, Local Impact. First part is a little bit about the science, which for time I'll skip through pretty quickly. Then talk about local conditions here of climate change. Then we're going to talk about some solutions. And then I'm going to show the last slide. It's about called thresholds and tipping points, what the future looks like and how it will impact us. So I'll jump right in here. So on this slide here, again, just for brevity, I'll move along. This is just the whole evolution of the Earth, and I have a couple of graphs marking prehistorically some of the climate trends that have gone on. I'm just going to point out some points here. The arrows are, we're just zooming in on the period, so we're telescoping in, getting closer and closer to the present. All I want to point out, in the past, we've had periods of warm and cold, but overall the planet keeps cooling with time. And then if you zoom into this little piece spread out, you can see since the last 66 million years ago, since the end of the dinosaur age, we've been slowly cooling. And we are in a period now that's comparable to the coldest period that was billions of years ago. And you'll see this here. So keep zooming in. This is 5 million years. And you can see we're down into what we call the Ice Age period, which has been lasting about 1 million years, where we've gone up and down out of interglacial and glacial periods. And you can see, this is an important point. We're going to watch the Eemian versus the Holocene. We're in the Holocene interglacial. The last big one was the Eemian, and we're getting close to be what is one of the warmest periods in the last 1 million years. So that's how fast our warming. And you can see now we'll telescope in. This is 120,000 years ago. We had Eemian. The last 20,000 years ago was our low point of the cold for our ice age that we had here. We're in the interglacial now, and it wants to cool. That's the next step, but we're shooting up warming because of greenhouse gases. But the important thing, we're going to come back to this, we're almost getting warm to the level of the Eemian. So in essence, we're going back to see what the weather was like 120,000 years ago. So we'll take a little closer. Again, I'm skimming through because of time, but if you have specific questions, just raise your hand and let me know. Let's look at the greenhouse gases. So as you're all familiar, we have seasons. We already have a climate. It gets winter, and we're in the middle of winter now. It gets summer. So the vegetation comes out north and south, and that's how you see with the carbon, there's the zigzag is the seasons. But you can see the exponential rise. And, you know, it's gone up all the way now. I got the latest numbers, 427 parts per million. And I remember when it passed 400. I remember when it passed 300. That's how old I am, when it was a big deal. But there's more to the story. It's not just carbon dioxide. There's also being released as methane and nitrous oxide. There's both natural and man-made processes that are released in all of these. And the challenge is, it took millions of years to put this into the ground, and we're doing it in hundreds of years. We're bringing it all up in 100 years. We're bringing out what took 1 million years to store. And the other thing to realize is we have the resident time real quick, and the what they call potential relative to CO2. So carbon dioxide takes about 1,000-year molecule to circulate through the atmosphere. That's our problem. It stays in the atmosphere once we release it up. Methane takes about 10 years, but it's 30 times as the absorption of carbon dioxide. Nitrous oxide stays up 100 years, and it's 273 times. And all your chlorofluorocarbons and hydrochlorofluorocarbons, they're tiny. They stay up about 140 years, but they're 4,750 times the absorption. These are really tiny amounts, but this is the one they banned because of the ozone. That's how dangerous it was. And these particular molecules get high in the atmosphere, so that's why they're very dangerous. They get lifted up. So when you combine them all, we have an index, or the CO2 equivalent, or they just call it the gas index, that shows if it was just carbon dioxide alone, we're actually dealing with all of them, and it's the equivalent of 523 parts per million equivalent to CO2. So that's important. It's a lot of pressure, not just CO2, but all the other gases are working to keep things increasing. So we look at on the atmospheric variables first, the atmosphere. This is the global temperature. It's climbing. This is only going to the early 2020s. I'll show you more. This is through 22. Notice this is where we are. We're in one of the warmer, but this has been really hammered as the Arctic, and Europe has really broken records. And there, you'll see on the most current data we have, you'll see this trend continues here. So this is some of the more recent data. This is the IRIS-5 data that's from Europe going up to 24. You can see the climbing. This here, it represents 5-year averages since 1850. You see that exponential rise. But this is to put everybody in panic. We broke the record in 2023 at 1.48. 2024 was 1.6. This is the critical line, 1.5. If you pass 1.5, keep consistent, you'll see on the last slide, it just spells irreversible changes. And this is the first year last year we cleared, every month cleared above 1.5. And you say, well, is it continuing? Well, yes. Not only was that the warmest year since 1850, but I got the January data came in was 1.75. So we're seeing now an exponential climb in the warming, and guess what? Here's your hotspots. Here's, you can see up in Europe again getting hit. It's that area up in the northern hemisphere right now. By the way, Alaska actually in January had parts that actually got above freezing during January. So that's how fast the warming is going. This is what you want to watch, is this average annual temperature relative to history, relative to the past.
John?
Yeah.
I don't know what you mean about the 1.75 and the 1.6 global surface. Can you describe what that
real
means?
quick. Go back. Yeah, you can go back. So what they do, they compare to a couple of references. They either compare to 1850 to 2000, or they take a 100-year comparison. But the idea is you take the average of all the annual data we have records for. Okay, and the reason to pick 1850, that's when instrumentation started.
Okay.
So we actually, and it's weak, there's a lot of noise early on, but they start there and then they just average it. And then every year they subtract from that average. So it's a deviation. So it's the difference from that average.
Okay.
And so you're doing small numbers now because you're taking an average and just the difference. And what they're watching is, what is that difference? That's what's increasing. You notice, if you take that average, this happens to be 100 years, we had cold periods all below that, couple of warm, cold, warm, and then just steady warm. That's what they're looking for, that trend. Okay,
Okay.
that makes sense? And this is just, the second one was just another showing you this. This went back to 1850, and the shading here is the noise in the data, but as we get closer, since 1980, we have satellites. So it's getting more and more and more accurate. We got the whole globe covered now. And same with sea level rise. We have very accurate data. And that's why it tightens up now. We know these numbers are real. And then the scary thing, again, is passing this 1.5 line. That's the deviation, the difference.
Okay.
All right?
Yeah.
Keep moving. So this is another really scary thing that came up. Started in 2023. You can barely see here, but there's a gray line. I couldn't get it to highlight, but I got the 24 to highlight. This is to give you an idea, these are references is 1991 to 20 and 1982 to 10. These are all the years over here going scattered. This is a spaghetti diagram, but this is what I want you to catch your eye. 23, we just broke out on sea surface temperature. We just went crazy warm. And it continued for 24, and this is the latest number that I pulled off that was available. It's almost climbing back up again. This is what freaked all the scientists out. All of a sudden, in the last 2 years, there was a huge leap in warming on the sea surface. And I want you to remember, let's cancel that off. I want you to remember, now, everybody don't panic yet.
Just do the,
I'm just shutting it. There we go. All right. I don't know where that arrow came from, but that's me. All right.
that's us.
All right. So they kind of panic. The thing you want to remember, this is absolutely important meteorology. The atmosphere takes on the characteristics of the underlying surface. So how the ocean goes, how the ice goes, how the land goes, that's what drives weather. Atmosphere itself is reactive. It's not proactive to anything else. So keep that in mind. So when that heats up, they start wearing. And so this is the superposition of carbon dioxide, and we're talking ocean now. We're focused on ocean. And you can see here, this is the carbon that's absorbed in the ocean. This is all measured at one location in Hawaii, Mauna Loa. And then you see the acidity going down as you put carbon dioxide. As you know, you're making soda. Carbon dioxide and water is seltzer. I mean, you're making soda. So what we're watching is, does this level off? Is there a maximum amount? Right now, it's still pushing down into the ocean. But globally, is there a maximum? Because once it can't go anymore in the ocean, it stays in the atmosphere. That's what they're watching. But even if it continues to go in the ocean, you've got increased acidity. That's going to be another whole set of problems. So we'll see that in a minute here. So this is a little close-up of the most recent data I could find. Again, same location, Mauna Loa, but you see there's monthly variation, and that's important. We're going to see everywhere. It's not just averages. There's a lot of noise just from seasonality, interaction of all the elements. You always have variation, so they average it, but you can see the trend more acidic all the way to 2023. And that's why, but you still have up and down. You'll see that through all the data. What does the acidity mean? Well, you're having oxygen goes down as being displaced by carbon dioxide, goes up, the pH goes down, and the mixing layers start getting smaller and smaller. So you're not getting the nutrient exchange in the atmosphere, and you're getting more radiance exposure. So that is really bad for marine life. For instance, the acidity destroys the shells of shellfish. Any kind of shellfish that you have, you'll end up dissolving it. They can't survive in this type of environment. And you bleach the corals. There's a bleach picture. This is a healthy one. It gets bleached. And that's what they're seeing in the tropics, where you're getting the heat, the radiation levels in the CO2. And that's something we have to worry about long-term here. Let's look at the ice. That's really the critical thing. Ice is very, very critical to the Earth because it reflects radiation. They have a term called the albedo, the amount of radiation reflected versus what strikes the Earth. And they use a ratio, so it's from 0 to 1. And when you have ice, you're reflecting 0.9. But when the ice is gone, it's like 0.2, 0.15. So everything gets absorbed. That's what we're worried. And here's what's going on. Every year, there's less ice. This is what, the yellow is what's typical. And every year it keeps shrinking. We have less ice covering the Arctic. And we have, and we have less ice in the Antarctic. In fact, we're near record levels this year of minimum ice on Antarctica. On the west end, the west side is what, the west shelf is what they're all watching, just breaking off pieces and going on. And you can see that that's where the loss is. There's very minimal on the east, but the loss, the yellow is where it's supposed to be or has been historically. And you can see it's just receding back. Remember, Arctic is an ocean, Antarctica is a continent, it's land. So there's a different dynamic going on. And the reason the Arctic speeds up in the north, because you've got mixing under the ice with the ocean, warm water gets in there. Continent's a little different. It's all piled up and it has to, like glaciers, it has to kind of roll off. This is Greenland. This is another critical. Greenland holds quite a bit of ice, as you're aware. And 2012 had a huge event where they lost it. This is the most recent data, 24 is the globe, but you still see a continuation melt days, the number of melt days. It's just getting smaller and smaller. And it has huge implications for us because the Labrador current, the fresh water gets in and mixed with the Gulf Stream. And that mixing brings cold, fresh water mixing with warm salt water, and it slows it down. It forces the salt water to go down. It comes as a surface wave. And you'll see that. We always have a cold spot up in the North Atlantic, north of us, and that affects our weather. So sea level, that's what what do we worry about? So again, 93, we had satellites that really did good measurements starting 93. And every year they're throwing up another satellite. So we're getting very accurate data now. But we didn't before. We had tide gauges, we had others. And so what you got for sea level, you've got three factors going. Thermal expansion, that you keep heating, the water heats and expands. Very minuscule relative to the other. You have melt. Greenland, glaciers, everything are melting water into the ocean. And then you have the added water that's going from the general melt going on all over the world. So you've got glacier melt, but the general melt, that's what's really contributing here. So I didn't want to get it confused. So thermal, this is mostly meltwater from glaciers from land. And then you got all the Arctic and Antarctic and Greenland are actually close to the ocean. These get put together, you can see the rise continues. This is centimeters, that's 100 millimeters. Keep that in mind in the next picture. There's your 100 millimeters. Right now, from the reference from 1993, again, they use it because they have good data, satellite from there. We've raised 4.5 inches since 93 to 24. And you can see this is the most latest data. And again, like all the data, there's a lot of other forces at play, so it's not a straight line going up. It's lower for a while, goes up. There's a lot of forces. I circled this for you. This is the East Coast. This is the fastest, one of the fastest rising areas in the world. We are moving, the rise here from 93 to this period here was 8 inches as opposed to the global average of 4.5. So it's not just uniform picture of water going up. It depends on the dynamics along different parts of the world, how fast it rises. So we're gonna now, you got the big picture, hopefully a little deep science, we're past that. Now we're gonna focus locally a little bit. So I didn't get a lot of data. There's not a lot of data, but in Long Island Sound, I did find some temperature data from multiple locations. This was pulled together by the Connecticut government, has, I think it's deep or somebody pulled it together. A couple of things keep your eye, and I'll explain the arrow. It's very erratic. You can see the data depending on how they sample. And again, they didn't have any record. Did they do it in April? I don't know. They could have done it all year. So it's pretty sloppy data. But what it shows is the trend going up. And the reason I've marked this, you'll see it on the data. This is from 2010. And if you notice, there's kind of a interaction, but then right after 2010, it starts in synchrony. The lowest part of they measured at the bottom, I'm sorry, the blue's at the bottom, the red's at the top of the water. They measure both the top and bottom. You see more rapid warming in the bottom mixing than at the top. And again, I'm not an oceanographer. I don't understand the dynamic. I'm just telling what the data. There's a warming, but you're gonna see there's an implication on the next slide. We're gonna look at that. This is the tide water. This is actually Bridgeport. You can get individual locations along. So I picked one just for the sake of time. But notice a slow climb, but then after 2010, a jump. Then it's climbing again, but it's all higher than previous, even though they average it together. And then this is, I caught, was really strange, excuse me. Was really strange. This is the cold water species. These are, up here is cold water, this is warm water, the black. And look, at 2010, all of a sudden it was a split. I mean, all of a sudden the cold water started going down and the warm water started going up. So you start in your mind, again, the data is very sparse. We don't have a lot of good data in the sound, but this is probably the best kept data they sample because it's at a location. They go out periodically. This was for a Long Island Sound study. They've been doing it every year, doing a mix. This has huge implications for us, telling us that the cold water is leaving species and we're getting taken over by warm water. And we got warm water coming at low levels. Well, the species are coming in with that lower warmth on the bottom, and we got the rise going slowly. Now, people are going to say, I want to go back because I think this is an important point. I want to show the sea level. The average 50-year, when you go back from 70, is 0.26 feet. And you say, oh, I don't get it. It's rising all this so many inches and everything. And part of the reason is, as you have the water rise, it erodes. It's eroding your coastline and it has more area to spread out. And it's changing the dynamics of inland water and the coastal water. So it's not like we have a glass sitting there and you're just pouring more water and it rises up. It's interacting where water hasn't been before and dissolving things and killing vegetation. And now all of a sudden the habitat's changing. So you got to be careful how you read it. That's still a lot, 0.2. You know, that's 5 inches, and you do the whatever it is, 3 or 4 inches, but it's still, it's more dynamic and you got to think it's more complex. And that's part of the challenge. Okay, moving along. So they just revised the number. They're now saying we are good to 2050 at 1.67 feet. That's the best number today that they're given when they figure all the stuff in. So, you know, again, translating that doesn't mean 1.60 all of a sudden in the Long Island. It just means we got a challenge, and I'll show you that. Real quick, you're all familiar with this. I just wanted to show that when you deal with water rising up, there's a lot of issues. There's storm surge, there's groundwater tables coming up. You've got the land sinking in our area to boot because of the last glacier. You've got tides, you've got waves, you've got sea level rise. It's very complex. Water on the coast is not just a simple picture. So here, this is a fun picture. Everybody like, this is when everybody runs up close to see where their house is. When I present this this is right now what typically happens, called the high mean high water. And you can see the blue is what they call the connected with the ocean. So the blue is connected with the ocean. Whatever the ocean does is blue. The green is not connected. Those are freshwater isolated. This is, it rises 2 feet. And I use 2 feet because it's inching up towards that, literally. It's probably going to be 2 feet by 2050 with all the changes going on. This means now all these light colored blue areas are now water. They're always there. This is not periodic. It is water there. And this is very familiar to the group here, where the study is. There's a lot of water that's going to be there. Now, what's really interesting, the next slide, and this was brought up by the people who did it. You know, when you have recent flooding here, when you have a really bad storm and you look at all the communities, how much flooding you have? 2050, that's every day. That's the standing water you can expect in the future, to give you a reference. This is stormwater today, when we have flooding. So if you got that puddle on Maple Avenue where Main Street is, or you got there, that's a permanent water body that's gonna be there in 2050. So anytime after a storm, you want to take a survey here and say, what is it gonna look like? That's what your house is gonna be surrounded by, whether you should get a boat or keep your car. Okay? So,
Little minutes.
so let's talk real quick solutions. We got three right now, we always talk. Retreat, rebuild, or recover. There's pros and cons for every one. Retreat, you eliminate the environmental risk, you're gone. Saves money in the long term, maybe than other options, keep building and protecting and doing everything. And the shoreline gets restored to a natural state, or it gets eroded, but it's back to its natural state, you're gone, man's out of there. Cons, psychological loss of not living on the shoreline. A lot of people won't sleep after that, they move out. Compensation may be less than the whole value being near the coast, moving away. And lack of desirable relocation sites. It's pretty hard just to find another site. I mean, you're competing. And I'll talk about that a little later. That's a major problem. Rebuild reduces flood risk, in most cases lowers insurance, at least on the West Coast they do. Residents can stay on a shoreline location, stay where they are. And in many cases, cheaper than relocating by lifting up your house, depending on your size of your house and how big it is. The cons, you still have a potential for future structural damage. You haven't eliminated that. Access to a home may be a problem. Yeah, you may be up on stilts, but you may have to climb down on your dinghy to get back, to get on land, all right? And subsurface, especially along the Connecticut coast, may not be suitable for rebuilding. We have an issue always with, you know, when you have the sands and the underlying strata, you gotta have the right base to put a support, and some places don't. So there's maybe not an option. Recover. Allows residents to remain on the shoreline, nobody moves. Return shoreline closer to the natural state. It's not going back to the original, but it's closer, it's in the right place. And it is resilient to climate change. Once put in, it has a buffer that no other solution has. The cons, living shoreline could be lost in a storm, especially if you're rushing to put one in, you get a major hurricane, it's gone. That's an investment. Cost for continued maintenance is not one and done. You got to always replant, you may have to re-add sand, there's work. And this is the biggie, as you know, in Chalker, interferes with shoreline access and view. People don't want to do it because, hey, I could just walk to my beach, I can see this, no, you lose some of that when you build because it's a buffer now to the water. Okay. Last slide. This is the scary one, so buckle up. All right. This was a big study done by a large group. What's going to happen in the future? Where is the world going to be and how is it going to impact us? So the big one is 2035, 2 degrees, and we are on target for that. I showed you the number, remember 1.75? We are on target for 2 degrees by 2035. 2035 is all these things which I'll explain happen all the way to here. And it's the yellow circles. And I'll read them off, you can't see it. West Antarctica, gone, collapsed. Labrador Gyre, subpolar gyre, gone, collapsed. All the ice, the water is melting now. The boreal permafrost thawed. More methane release, more going on there. Barents sea ice lost. Low level coral reefs all dead along the tropics. That's why 2035. If you move up, now slide over, which we're on track for, to 2 to 4, which 2045 is the start of that, and it goes to 2075. Now I'll be pushing up daisies then, but the rest of you guys will probably be here to see this. All right. Mountain glaciers lost. Amazon forest dieback, by the way, this has started. There's a drying out here and the Sahel is gonna green up. The Sahel is actually gonna stop being a desert and actually get vegetated again. Because we have a permanent change in atmospheric circulation. Irreversible change. Once it kicks over, after 2035, we're in a whole new regime. No quasi anymore, we're in a new regime. Remember that 120,000 years ago? That's what we're going back to, what the circulation was then. Okay, then also not pushed here, but another one they're looking at, a permanent desert in the Southwest. A lack of water for 100 years, if it dries up, like they're predicting happen. There'll be very little water in the Southwest. We're talking New Mexico, Arizona, Nevada, those areas gonna be dry. And then you got the big one, now this is the big debate one, is the Atlantic, which affects off the Gulf Stream. They call it the Atlantic Meridional Flow, okay, the Gulf Stream. That's the one that people are debating. I just saw a new paper just came out, get this, they see it collapsing by 2045 now, they moved it up. They actually moved it to this other side. That is a huge implication for us. If that slows down, all of Northern Europe, England get cold. They rely on that warmth coming up from the ocean. And if it slows down, we get warm because now the heat is not being transported as fast. It's being stuck right off our coast. Remember that warming underneath? We get warmer faster. Remember the water temperature is the key? Everything changes all of a sudden. And that's one that they're watching very carefully. And again, I won't for the sake of time, but we can go through the others, but step by step by step, all the ice leaves the earth by 2045, it's gone. We have seasonal ice by 2035. We still have winter ice and we still have the Antarctica. But by 2045, the Arctic is completely all year round, has no ice. Remember that albedo? Changes everything, speeds up the warming, speeds up everything. So the consensus, I'll stop here and take questions. I know I had to rush because of the time. The consensus is right now that this change is not going to stop. It's irreversible. We've waited too long. We are easily going to pass the 2-degree mark, no matter what we do. If we stop today and did everything, we are not going to get 2. We can prevent 4, slow that down, but 2 is going to happen. So the future generations are going to have to live with this changes, and it's not pretty. I mean, it's a different world. Again, things will be different. There'll be some new winners. You can now maybe, grow wine up in Quebec, but it's going to be changed. So this is my apocalyptic side. I always put at the end. That's why I get the term Dr. Doom. So anyway, I'll stop here and answer any questions for a few minutes.
So Joe, why is it important for zoning, planning, and the commission to know this?
It's
Why?
it's very important because every inch you fill in, every inch you put a wall, you're pushing the water. It has no place to go. It's gonna go on somebody else's lawn, and they're gonna put a wall, and they're gonna fill in, and it's just gonna keep pushing. And guess what? Now you're hitting more and more homes, unless the whole place starts trying to build a thing, which you're still not gonna win. But that's why it's important. You've gotta let nature do its balance. You gotta let the water flow, and you gotta allow space for it. I don't know if you want to add anything to that, Carol, but
Well,
that's.
no, that's my concern is, there's just so many requests for variances and construction and removals within 100 feet of the wetlands.
Yes,
And and cutting down trees, all of that, trees
All-
cut up the water.
trees, vegetation is your biggest friend, trees.
Right.
That's what saves sand, that's what saves everything is trees, because they hold everything together. Every one you take down, and guess what? Trees take up in carbon dioxide, so you're destroying. By the way, salt marshes are the most efficient vegetation ecosystem in the world for absorbing carbon dioxide, even better than forests. It's very efficient. And it's just the nature of the mix of vegetation that's in it. So we're we're part of the solution here if we can keep ecosystem, if we can keep our salt marshes healthy and doing it. And you know, as Chris knows on the study book, and there's mud flats now. There's dead marshes, which is absurd.
Here in Old Saybrook.
In Old
Yes,
Saybrook,
there
there's
are.
dead
Yes,
marshes.
there are, because of what we've allowed.
Because people filled in. I mean,
Yes,
I don't want to pick on Chocolate Beach real quick, but Terrence, you know, there was natural outlets for all your water to the beach. And in the 1920s and 30s, they filled them in and only allowed a couple of paths. And guess what? They starved one marsh where it can't even replenish correctly. And that's what happens. And we have to reverse this. That's why I'm in favor of recovery.
And just to comment on really what Carol said, and I've spoken to many committees, zoning, inland wetlands, and I've asked the question with a lot of these decisions for development is, have you taken into account climate change, what it's gonna look like in 10, 15, 20 years? I don't use your specific dates, and the answer is always no. So that this is not taken into account when decisions are made for, but we're not looking to stop development, but you need to understand what's development.
That's a really,
In 20 years, because I've seen it at Chocolate Beach, I won't say how many years, but 5, 6 decades. The one marsh that has all the water from Route 1 dump into it and it exits, it's not a cold tidal marsh, it exits to a 24-inch pipe, literally millions of gallons of water. So it's a gulp, it's a gulp cup from 7-Eleven with a pinhole in the bottom. And I know Doug's is presented. So that's always a concern. And I asked the question, or we asked the question on part of the coalition, has these decisions making for changes, adjustments, things bypass, have you taken into account what the science is now showing?
yeah,
And the answer is no.
no, and that's, that's what zoning should be looking at, is 2050. Saying we should zone and plan for that, because that's coming up 35 is 10 years. I mean, that's not far.
Inland wetlands too, because that's the big one
Yes.
that we
All of
spent
it.
a
They
lot
have
of
to-
time on is inland wetlands.
Exactly, they gotta start thinking like that. Real quick, as one of the solutions, when I lived in upstate New York, they set up a tax system that if you used land appropriately, your taxes were low. But if you wanted to take the most fertile farmland and build on it, your taxes were through the roof, because it was farmland. But if you wanted to put in an old pit that, was an old road access or something, your taxes were low, because it was an appropriate use. That's something maybe in Old Saybrook we should look at. The appropriate use of your resources is how much tax you pay. If you're a good steward, you should be paying a lot, because you're contributing to the health of the ecosystems of the community. But if you want to go knock trees down and fill up marshes, you should be taxed through the roof. If you're allowed to do it, you should be taxed through the roof for that.
Dennis has a question.
Sure.
Excellent. Thank you. Yeah. Excellent presentation. I would just personally want to highlight in our town, in Old Saybrook, as we look at this sea level rise, these water issues, kind of the whole gamut that's been presented, they inordinately affect the land 5, where the vast majority of our population, our housing, our businesses are. And so the question as to why is this important to planning and zoning, what's happening with the planet is the way I look at it is because we need to prepare, as you said, 2035 is right around the corner. We need to prepare the town for how these changes are going to happen. What's going to be done? Where are things going to be going? And so that's just my 2 cents and how it inordinately affects the southern part of town.
Yeah, and to follow up on what you're saying, and Carol brings this all the time. Do you think it's a coastal issue? The coast is actually better. It's behind the coast. It's the rest of the town is gonna be the one getting
Correct.
That's where all the water is gonna be. The coast actually can build up. I mean, we know we have 12-foot barrier, but Main Street's 2 feet? 2 feet above sea level?
Low.
It's low. I mean, so Main Street will flood probably before we will even know it on the coast there. So keep in mind, we're all in the same boat, excuse the pun here, but we're all in the same boat for Old Saybrook. Everybody's affected, everybody.
So Joe, were you gonna touch on the coastal resilience coalition?
Yes,
Just
real
wanna make
quick,
sure.
yeah, we got a couple minutes. So we have all the beaches working together. And we formed, formally in 2023, we formed a nonprofit corporation called Old Saybrook Coastal Resilience Coalition, Inc. now, I guess. And the idea there is, in fact, I brought some handouts, so it has this in here, by the way. It has the complete description of what we do and what we came up with, but in a nutshell, what we do is through meetings, we've identified, prioritized problems among all the beaches. Chalker Beach being one of the big ones, Benwood Seawall, another one. And then we look at supporting grants, which is why we're represented with Chris on this new proposal, so we have to have some input. And then we go for donors or whatever, looking for resources so we can actually do something. You know, we do a lot of planning and we do a lot of talking, but we gotta start doing stuff. And that's why we got together. And it's open to anybody. It's not just for the shoreline. We have, now we have guests we call affiliates that come in, and retired people. We have an operating engineer. Doug's an engineer. He's affiliate with the county. So we have other resources, and actually we're quite proud. We're building up a big expertise base that's building up in there that we can tap. But that's our goal here is, we have the saying in there. We have the saying, planning, permitting, and performance. That's how we like to say it. We're always at the planning stage, but now we gotta get to the permitting stage, and the real win is the performance. We gotta actually do stuff. And that's what we're all pushing. Hopefully, before we're all gone, we'll get something done. So that's the goal.
And just in Joe's handout, he does, I'd ask everyone to take it, there's a picture of a street in Chalker Beach, I think it's right there.
Yeah.
Just
Yeah, let me
understand,
pass it
that is not salt water, that is fresh water from flooding, storm water. That's about.
Yeah, let's pass it
100
around.
feet from the Long Island Sound, that flooding of those homes there is all fresh water.
Yeah, that's a
Mostly
good.
off of Route 1.
Yeah, on the one side is, the back side is all about the coalition. On the front is our plans for living, why we are advocating a living shoreline, what the benefits are, and why we're big on that. That's what we're trying to do. You got enough there? I can pick up one direct.
There's another.
Up there. But it's got some cool pictures. The one on the back that parents is Chalker Beach.
That's storm water, that is not Long Island Sound water. We test it, Chalker Beach tests the water.
So it's not salt water.
It's not, it's very low salinity.
It's fresh water
Fresh water.
waiting to drain out through the tide.
24-inch pipe.
And the reason it says
Oh, yeah.
constellation on
How
it
many beaches? I got
Because we
some.
got
they
a
gave
grant.
the coalition
This
a
is
grant,
from a grant.
Folks
from
going
the
out there?
foundation.
You got enough? You want
I can
extra?
make copies.
All right.
which was good use of that, those funds.
So back on the back side, you see Chalker. Swimming.
That was January 2023, 13 months ago.
There you go. Just a little bit.
I do what I've been meaning to mention to Joe. I was looking at my phone because maybe something your group would want to comment on, but there's currently a House Bill 6249 to authorize residents in a flood zone to lay 10,000 yards of landscaping fill a year in their yard and get a tax deduction for the cost of such fill and a grant program for road raising.
Oh, wow.
It's a joke, right?
Oh, no, it's
No,
serious.
that was real.
So the Connecticut Association of Zoning Officers, I'm in their executive committee. And so we watch these bills and they're like, here, Chris, this is one, it's in
Oh,
something you might be interested in. So isn't that ridiculous?
Yeah.
Yes, very.
so the threat is real. That's all I'm saying. And as a town, you know, I think you have a little fight because you guys started thinking of this, what, 2018 or even?
2014 was our
2014.
first sea level rise report.
Yeah, so it's been almost 11 years. So you've been conscious of it. But time is running out. That's all I can say to get things done. That's all. That's the end message. All right?
Thank you very much.